workshop coming up later this month, Appian Part 1. So the course is primarily geared towards the concept and theory of the course in terms of learning how to do processing. Appian Part 1 and 2 focus on single particle, and Appian Part 3 focuses on tomography. Part 1 is scheduled for January 30th. It's not part of the course. If you're interested in learning more about the processing, you can sign up for that. Part 2 is March 8th, and then tomography is later in March. Our recitation sections will begin next week. Next Wednesday, we'll actually meet downstairs for the recitation, and that's going to be a journal club. 2 weeks from now, we'll have a companion recitation that'll be more of a practical. So a lot of what we'll be covering today about the microscope parts will hopefully be a little bit easier and will make more sense as you go to a microscope and see the parts as well. But we're sort of doing things in the order of the Jensen lectures going on. Any other questions? We will be posting as much as we can in terms of the YouTube. I think we will post the unhearable, unaudible lectures as well, just so we have a complete series. But if you are absent taking the course for credit, please notify our TAs. Any other questions? No? Okay. So today we have a staff member here, Laura Kim, and she'll be telling you a lot about the ins and outs of microscopes, especially microscope parts. And this is crucial in the sense that if you're an artist, you want to know the tools of your trade. And in terms of EM, they are quite critical because a lot is glossed over. There are a lot of things that are very similar to physics and optics, but there are certain things that are different, and we'll cover that quite shortly. So I'll give it to Laura, so you have to click that. You just like yourself, right?
Yeah.
Okay. I'll probably drop the microphone.
Okay, can you guys hear me? Okay. Carl, are these showing? Not yet, right?
No. The projector's not on?
It's, oh no, I didn't know.
Always, we'll never start on time.
While he's figuring that out, these are just slides actually directly from the Grant Jensen lecture course. So I know that Yangzi sent you guys a laundry list of like 10 to 20 minute videos off of YouTube. I find them super helpful. Most of the people I know in Cryo-EM all find them extremely helpful. So if you haven't seen them yet, it's very digestible. Just go check out the links. Basically, these slides actually come from his website, which condense every single lecture that Yangzi sent you guys. So we'll just go through each section in like 2-3 slides, do the concept check at the end of each of those sections, and so I'll just answer all the questions. Feel free to kind of chime in if you have any questions or things are unclear. Hopefully I won't butcher any of the topics too much. Some areas I'm more expert at than in others, so I'm sure Ed and Micah and hopefully Yangzi will chime in as well. Just waiting. Yeah, so the slides will be available online, but they're just directly taken from the PDF from Grant Jensen's website.
Plugging on plugging.
I didn't plug anything in. This is going through the present, the presenter desktop.
Should be an HDMI cable.
Yes.
Yes. You just want plain HDMI. Then you would take this out. Yeah.
Sorry, I thought this was going through some Wi-Fi. Okay.
Near your screen is
There we go. And let's do that. Okay. So again, my name is Laura. Again, feel free to ask any questions on the fly. This is very sort of informal, so the way we'll go.
very temperamental.
So, Ed, the problem is that now I can't see that window again.
You can mirror your screen. You go to settings.
Probably because the projector is now a different desktop.
Yeah, I can't find that desktop. Come on.
See your pointer. It's on the other
Yeah,
screen.
and the slide desk was there.
It's good settings. Just mirror displays.
Okay. Now I just have to find those slides.
Whatever they want.
Yeah. Okay. All right. So the first section that he starts with is electrons. Why do we use electrons as our source of radiation as opposed to X-rays, photons for light microscopy? And it's actually pretty simple for us. They have a very, very small wavelength. So over here, he kind of just parses out all the pros and the cons of both visible light, so photons, X-rays, electrons, and neutrons. And primarily, one of the strongest features of electrons is that, one, they can be focused through a series of lenses, and then also they're very, very small wavelength, smaller than the wavelength of X-rays, which are in the angstrom range, which is 1 to the minus 10 meters, whereas picometers are 1 to the minus 12. So that's 1/100th of the wavelength of an X-ray. So we're not limited in resolution by the wavelength of our electrons. Some of the cons, though, of electrons is that they are pretty damaging to the sample, so we have to work in what's called low dose mode for data collection. But also there's poor penetration, so that's one of like the why it's called transmission electron microscopy, is that the transmission has to happen below a threshold of 500 nanometers. So if your sample is thicker than 500 nanometers, which typically in Cryo-EM it is not, it's more like in the 100 nanometer range, then the electrons can't penetrate it, and then you get no signal. So poor penetration. He also talks about this sort of structural biology continuum, and most of structural biology, when it's kind of mentioned offhand, most people are usually referring to X-ray crystallography and NMR spectroscopy. And there's obviously this new resolution revolution that's kind of put Cryo-EM at the forefront of all of that, mostly because it actually serves this really nice niche between like high resolution structure determination and kind of answering more of like the more macroscopic level questions we have about proteins and how they interact in like systems and in organelles, and also being able to have targets like complexes, which kind of fall apart for crystallization for Cryo-EM. For X-ray crystallography. So that's one of like the sort of really nice things about Cryo-EM is how flexible it is as a tool for structure determination. We can work anywhere from kind of like the 100-ish kilodalton range up to megadaltons for ribosomes and large complexes like that, with the help of phase plates, energy filters, and other things that we'll talk about today. So concept check. Advantages and disadvantages of electrons compared to photons. Again, electrons have a small wavelength, whereas photons for light microscopy are more in the 200 and 400 nanometer range. But photons are they don't damage your sample as much as electrons do. Neutrons, they haven't figured out the technology yet to create a focused beam and bright beam of neutrons, so that technology doesn't exist yet, but maybe in the future one day it will, because neutrons also have a very small wavelength and also are very, very low damage to the sample. Structural biology technologies that give higher resolution than Cryo-EM, X-ray crystallography, NMR spectroscopy, and then also molecular dynamic simulation, which is like looking at the atom-to-atom level sort of kinetics of a system. And then for the lower resolution, we have cryo-ET, electron tomography, where we're looking at sort of slices of what could be whole cells, and they kind of answer the in-between of high resolution and sort of macroscopic questions in biology. So this cartoon is a schematic, sort of more of like the top part of an electron microscope, which is our electron gun. So at the top here we have our filament, which is usually going to be some pointed, bent wire or some sharpened like crystal where electrons are kind of just sitting up here being excited. And what pulls them down are a series of different things. First off is this, what's called a Weneld cup, or this shield, Weneld cylinder. It's basically a little bit more negative than the electrons inside of the filament, so it helps to pull the electrons off of the tip of your filament. And then it helps to kind of like focus, the Weneld cup helps to like focus the beams that get sprayed out of the electron tip, the gun tip. Then it goes through a series of different lenses and condensers that bring, and accelerator stacks that bring the beam down to our anode, which is sort of like a positively charged, attracting surface for the electrons to come down on. There are 3 different types of electron guns, and I'm using guns because we only refer to a gun for a field emission gun, but sources. First are the tungsten filaments, the Lab 6 crystals, and the field emission guns, and I'll go into more detail 2 slides down. So this is actually a really, really good part, and I think if you do anything in EM, just do this part. Like, learn this part. It helps so much with all the other components of the microscope. So, so first off, he shows this filament, this bent filament that has electrons going through it at an energy of 300,000 volts. And then this is the Weneld cup, which is a little bit more negative, which is this minus delta than the electrons from this source. The Weneld cup also produces this electric field, which is shown with these little red dots that help to focus that spray of electrons. Sorry, I'm just going back and forth for my notes a little bit. Focus the initial spray of electrons. The next feature that the electrons go through is what's called this accelerator stack, and he draws 10 of these accelerator stacks, and they're basically just discs with holes in them, and they're connected by resistors that create this graded potential that help to create these perpendicular magnetic fields, and in red right here across the accelerator stack, that help to accelerate your beam through the accelerator stack that emerges onto your sample. So one of the important features of this graded potential is that you experience basically 300,000 volts of electrons down at the plane of like your sample. The speed, for instance, for a 300 kV microscope is that the electrons are accelerated at 76% of the speed of light. So, and the wavelength of those electrons are about, it's a little bit less than 2 picometers. So again, resolution is not limited by the wavelength of your electrons. Next thing to refer to is, this is more of a safety thing, but he mentions this sulfur hexafluoride, which is this odorless gas that kind of jackets the high tension tank where the electrons are coming out of. It's a safety issue in that it's an odorless gas, so if there's any leak in your high tension system, in your compressed gas, like nitrogen gas, it is heavier than air, and so it could end up sitting sort of harmlessly at the base level of your electron microscope room, and in any like disaster scenario, someone gets knocked unconscious and they fall asleep inside the room, then they could asphyxiate. So there are a lot of EM centers like ours, where in EM rooms where you have oxygen centers that are planted at the floor levels just to make sure you're maintaining a healthy amount of oxygen in the room. Next thing that's important to kind of conceptualize is coherence of your beam. So when you're thinking about your electrons being emitted from your source, there are 2 types of coherence, which are spatial and temporal. And I really like the way he was describing this. So spatial coherence is when all the electrons come down in the same direction and in the same position. So if you have, your electrons coming down and they hit your sample and then they hit your detector down here. But then if you have something spraying your electrons and it's coming in this angle, hits your sample, but now it hits a different point on your sensor, now you're gonna average those out and it's gonna blur your image, and that's what is poor spatial coherence. So you wanna make sure all of your electrons are coming down parallel in the same position. Similarly, temporal coherence is, do they all have the same speed? So if not all of the electrons having the same speed of 300,000 volts, then they'll get focused differently by the lenses, and then they will also get smeared in your final image product. So again, that's poor temporal coherence. So you want to make sure that all of your electrons are emitted from your source with the same energy. Here are some images of actual filaments. So again, it's just a bent wire where electrons are just being emitted from, and then they're pulled from a source, sometimes actively and sometimes passively. The first one is a tungsten filament, which is just a bent tungsten wire. The pros and cons of that are, one, they're very cheap and easy to replace, especially on screening scopes, where you just kind of want to use it as like a workhorse for screening and things like that. Similar to that is the Lab 6, the lanthanum hexaboride crystal. The pro of this Lab 6 crystal is that it has a very, very sharp tip, and so the electrons emitted from this source have more coherence. Next is our field emission gun. So the field emission gun is a little bit special in that what ends up happening is below the tip of the gun, the tip where the electrons are being emitted, an electric field is applied to it, and that kind of gives it more, one of the main features of this FEG is that and I don't think this is actually related, I'm going tangentially off of it, but it has a higher coherence, and it also is more stable inside of the vacuum. But field emission guns are very, very expensive to maintain, and they're quite, like, all of these, you have to apply some amount of heat to them, and so the lifetime kind of varies, and so it can be sort of like a subjective manner to kind of take care of them, so you just want to make sure that the emission and everything, it all looks right in the heating of these sources. Filaments require regular heating, but so it's tempting, I think, to like warm your filament to be warmer, so you have a brighter beam, but it also degrades the quality of that tip more rapidly. So just finding the right temperature to operate your electron source at. Okay. First one's pretty obvious. Where do the imaging electrons in an electron microscope come from? They come from the gun or the filament, the electron source. What part of the gun is called the cathode? The cathode would be the filament itself, and then the anode would be sort of ground level, so that's when the electrons are coming down to ground in that accelerated potential down at ground. What is the accelerator stack a stack of? A series of disks with holes in them connected by a series of resistors, creating a graded potential. Typical voltages uses for TEMs, we have anything from 80 kV, 120 kV, 200 kV, and 300 kV. I don't think that there's anything outside of those. Youngsi?
I mean, I think there is one higher one, like a 500 and
Oh.
Then it's a million.
Million,
Like a
okay.
million volt.
Oh wow, I did not know. So 1,000
Extremely
kV.
unstable.
Oh, okay. I've never even heard of that. So there's a variety of accelerating voltages that you could be working at. And each of these, so for 100 kV, the wavelength of that electron would be 3.7 picometers. 200 kV, it's 2.5 picometers. At 300 kV, 1.97. So it gets successively smaller, that wavelength, as the speed increases. What does it mean to condition the gun? It's when you run the accelerating speed, like the high tension, at higher than it's operating, and so you get what's kind of like a discharge of the system, and then you take it back down to its normal operating. So it's kind of like to stabilize the system by ramping it up a little bit. It's not something that's done regularly, at least for me, in my experience. Difference between spatial and temporal coherence, so making sure your electrons are hitting the same position all the time versus the speed of those electrons. And you want both of those to occur. Three main types of guns. We have a FEG, a field emission gun, a Lab 6 crystal, and a tungsten filament. A tungsten filament and a Lab 6 are pretty much always going to be sort of on your lower end scopes. and they are cheaper to operate, but less stable, and conversely a FEG is more stable and higher coherence. Alright, so lenses, primary thing that, so this is a cartoon of a glass lens. So as photons are being scattered off of an object, they get focused by this glass lens here, which what happens is that the wavelength gets compressed and then it comes out being bent again towards this imaging plane. And the main important thing for this is to talk about, and also they bend and focus your beam source, your light source, but they can also introduce magnification. And I'm not going to go into this, mostly just these two equations below, which are called, which one is the magnification, which is just the length between the central plane of your lens, the length between the central plane and your image as a ratio over the length between the central plane and the object. And then what's below that is what's called the thin lens equation, which relates the focal distance right here to these two lengths right here. Not super important for today. This is, so now relating your lenses, your glass lenses, to how an electron lens works. So the way an electron lens works is a little bit different. What you have are these wires that are like kind of coiled together, and you apply a current to them. And once that current is applied to the coil, it creates a magnetic field around that. And those magnetic fields are what focus your electrons. And so when you have electrons coming off of, scattered off of your object, your sample, and it just goes along the optical axis like this, they don't get bent in any way. It's when they are scattered off of that axis that they get bent in this solenoid sort of trajectory, creating this image over here. So electron lenses focus images by creating this magnetic field that bend your imaging electrons. Okay. So he mentions there are 4 parts to an EM lens system. So in this diagram, we have your incoming electron source. So your electron source will never be coming straight down. It will be some physical object spraying off electrons, and the rest of the system, what it does is it helps to center that down some optical path. And that's why we have all of these deflectors and lens systems, apertures to kind of correct for that. So the first thing, so here's your lens, and so this is where our magnetic field is being applied to focus our beam. The first thing above that is what's called a deflector pair, and what these do is they tilt and shift the beam. So the first pair on the top will tilt and then shift your beam to, and that's like kind of like a first step at the top of your electron source. After that, you have what's called a stigmator, and so what that does is all lenses are not perfectly equal and all the way symmetric along all sides of it, so it doesn't always create an even magnetic field around it, which means you have to correct for that by compensating with these stigmators. And what they do is they just conversely add or subtract more field, more current to correct for imperfections here. And then finally below that we have an aperture that will remove electrons that are very, very far from the optical axis. So anything that is, spraying outside of here will be chopped off by our aperture. We can make this a little bit more interactive if you guys want. So defining property of a lens. Anyone? So they focus your radiation source. how do optical lenses focus light? By refraction. So they bend the photons within the glass, and then they bend them to imaging plane. We're not going to draw a diagram to show how the lens works. But the parameters that determine magnification is the focal length, and then also the distance between the lens, the fraction of the distance between the lens plane and the object, and the lens plane and the image. So that's what the actual, how magnification is calculated. Electron lenses focus electrons by bending electrons with this magnetic field. Why do electrons, images rotate? Oh, this was actually, I don't know if this is something actually Ed or Yangzi or Micah might know, but why do electron images rotate in an electron lens?
If you look at the diagram earlier, it's when this one actually, your electron actually turns around when it goes through the lens. So depending on how much force you put it on, the whole image will actually rotate when it goes through each lens series. So we have to, so you have to kind of take account of that when the lens actually rotates your whole image.
So if you think about an electron going through a magnet, if current, electron, it spins. So really your electron is going like this down the column. Something else that's particular for a TEM lens, your sample is more or less in a fixed location. You have some play. Your lenses are pretty much fixed, and where you're projecting is fixed. So our microscopes aren't continuous magnification microscopes.
Mm-hmm.
They're set magnifications you have, and depending on, usually those magnifications from the manufacturer keep the image more or less in a reasonable rotation where it's always in a particular direction. You can get additional lens series that give you intermediate mags. In that case, you'll note that they'll be rotated. So you might see an object in one mag and another mag will be rotated because of that.
And practically speaking, so you actually do see this in the microscope too. When you start at low mag and you go to higher and higher, you start to see your image start to rotate up the plane. So I think that the microscope has some calibrations within to kind of correct for that, but it won't be like 100% perfect. But it's something to keep in mind as you're like going through a series of mags. Okay. 4 components of an electron lens system: the EM lens, the deflector pairs that shift and tilt the beam, stigmators which apply variable current to compensate for asymmetries in the original magnetic field, and then the aperture to block radiation that's very far from the optical axis. Okay, so next we have here, this is also a really nice diagram because it actually shows you, Micah, I thought this was kind of helpful. So this diagram actually shows you, on the left, the 3 different sort of lens systems of a microscope, and then on the right, the corresponding buttons and knobs that the microscope actually, what it's actually correcting for when you're messing with the intensity or the spot size. So this is actually a really good reference point if you ever are wondering what you're doing on the microscope, what you're actually controlling. So the three parts, the primary parts are the condenser system, and that focuses the electrons coming from the gun to the sample. It's right here. Next, we have our objective lens system, and that produces magnification in the sample. And then the projector lens system, which further magnifies the sample. So, some things that I found relevant in here is intensity. So the intensity of your beam is being controlled by what's called, so this would be our C1 lens and our C2 lens. A lot of microscopes have these 2 condenser lens systems. Some have only 1, some have 3. So the more condenser lenses you have, I think it helps with the coherence of your beam as well. But the Cryoses, for instance, are 3 condenser lens systems, whereas like your T12 is a 1 condenser lens system. So yeah, intensity is controlled by your C2 in this diagram. Your focus, how you're focusing your images, are controlled by your objective lenses. And your magnification is at like, I think more of the broad scale is controlled by what's called these intermediate lenses. So this would be I1, I2, and then your what's called the projector lens. So when you're running through, there are three sort of like modes of magnification: LM, M, and SA. So that's low mag, mag, and selected aperture mags. And so when you're running in any of these modes, especially, so when you're in SA, these are all of your high mag modes, you're running current through all three of these lenses here. But when you start going into LM or M, you're turning off one of these lenses. So it's important to know that when you're like applying a current to a lens on and off, it changes a lot of things internally in the system, which can introduce a level of hysteresis. So it's very important. One of the things here at the facility that we always encourage users is when you're leaving the microscope, always leave it at SA mode, so that all of the lenses have current being applied to it. Because once that's off for an extended amount of time, there's a lot of hysteresis in the system. So just an important thing to kind of keep in mind.
We'll be going through, obviously not all of these,
Mhm.
because that would be a lot.
Yeah.
But some of them during the microscope practical on the 31st. So we'll get to mess with the gun deflectors and the
Mhm.
condenser apertures, fiddle with them and see what impact it has on the beam,
Mhm.
what impact it has on the sample.
Mhm.
So you guys can get sort of more hands-on conceptual understanding of the various parts of the microscope that we think are, well, that we have enough time to go over.
Yeah. Okay. This is where he just talks about different layers of magnification created through the system with the objective lens and the projector lenses. So pivot points. So the pivot point is very, very important in the alignment of the microscope. What it helps to control is to make sure it sets a point inside of the beam. It sets a point within the tilt of the beam so that you make sure that you can control the deflectors so that they can tilt and shift your beam independent of one another. And so that's what a pivot point is. That's probably not very helpful for you unless you're like looking at a microscope and what it does, but it's a very, very important alignment to do. Ed, Young-Z, I don't know if you guys have anything you want to add to that. No? Okay.
Is it like, is there a response when does it detect the fact that it's hitting a certain point, like,
So when you're-
and then respond to that, or is it just a keep image?
So most of these alignments are kind of done electronically through the system. So you set your sample to what's eucentric height and eucentric focus, and then you go through like these series of alignments just through the system, and then you'll see basically a shift in your beam, and you just want to minimize that shift in the beam. So until the point where they converge, and that's the point where I guess the gun deflector is able to shift and tilt your beam independent of one another. So this is all a lot more helpful if you're on a microscope too.
Right, but it's more the processing is supposed to like.
It's not a processing thing. Yeah, this is at the hardware level. Yeah, we're talking about the beam at the microscope level. So I don't think that this is something you would be able to see in your images. Like I don't think you'd be able to identify in a bad image that was a pivot point issue.
Right, that it's
There's so many other
extracted.
things that can happen that go wrong that make the image look bad. Only a few things where everything can go right and the image looks really good. So calibration, he talks about a calibration versus an alignment. I think as scientists, you guys kind of know what a calibration is. It's something internal in the system that you want to make sure is correct before you do any external alignments to that set standard. He talks about hysteresis. So this is like a word that's thrown around pretty regularly in EM. What it means is, and this is the first time I actually learned like a definition of it, is that as you are applying, so in this XY diagram, you have here the magnetic field of your lens, and then the current that you apply to your lenses. So as you apply more current, you get more of a field. But as you go increasing in current, it doesn't behave the same way as you decrease the current. And that's this difference is that hysteresis. So as you're going through different like mag series and applying lens current in certain lenses versus others, this is kind of like what it graphically looks like. So he mentions going from like high mag at 32K versus 19K to 5, kind of what experience is. And so you can do this thing called normalize to your lenses. And so what that does, it runs a current, so you have your original current that you're running your lenses at, and then it runs it above it, and then below it, and then back to the original lens. So it kind of like creates like some middle ground area, and that's what normalizing your lenses does. It's just to help to minimize the hysteresis in your lenses. Okay.
I had a quick addition to that.
Yeah.
Something that Laura and I found out thanks to Bill, one of our scientists here. So the hysteresis gets introduced when you change the amount of current going through the lens system. The temperature changes, so the resistivity of the wiring changes. Bill was telling us that on the Cryoses, and he thinks it's just an FEI thing, the company that manufactures Cryos, that it's to change the magnetic field instead of varying the amount of current in the lens system. So like a hysteresis plot, instead of increasing or decreasing the amount of current in FEI's lenses, they just apply a current going the other direction to modify the magnetic field so that the amount of current in the lens system stays constant, and it minimizes the hysteresis that they experience in their lenses.
Which is
kind of cool.
Yeah, which is probably why the Cryos is, again, another feature that it has that makes it more stable and consistent than other electron microscopes. Hold on, I'm just going to go through these and see if I can, through the important ones. I have until 4:35. Okay.
You don't have to take that long.
No, I don't want to. I know this is kind of dry. 3 main lens systems, the condenser lens system, the objective lens system, the projector lens system, the conjugate plane, or the different planes at which the image is formed after it's magnified through the different, like the lens systems. To the 3 independent sets of deflectors. The gun deflector, which is in the condenser system, the beam deflector, which is in the objective, and the image deflector, which is in the projection system. This is the filament knob controls the intensity. The filament knob controls how hot the filament gets. The emission button controls the difference between the Wenelt, which is the minus delta of the electron source itself. So that's what the emission controls, the difference between those two values. Spot size is controlled by your condenser lenses. The intensity is also controlled by your condenser, but your condenser lens too. Focus is controlled by your objective lens, and magnification by your projector and also your objective lenses. What's controlled by the high tension knob, the voltage drop across the accelerator stack. A crossover is the point at which electrons converge. Which knob controls whether the microscope is an LM, M, or SA. That's your magnification knob. And what currents change. So this is when I mentioned, the 3 lenses in the projector system, your I1, your I2, and your projector lens. So whether all 3 of these are on, or 2 or 1 controls the low mag, mag, and SA mags. Pivot point is the point around which the beam will pivot to enable the double deflection coils to accomplish a pure shift and a pure tilt, independent of one another. Hysteresis, when the magnetic field doesn't behave similarly going up in current as when it is going down in current. Okay, that looks good. Sample chamber. Okay, main important things of this that I found is actually just going through the questions, which is so practically speaking, when we're going through and training users on the F20 or the T12, we have 2 different components, which is right here. This component right here is controlled by what's called like a turbomolecular pump, and so, or an airlock. And what that does is it's kind of like this pre-vacuum before your specimen enters the actual column, which is right here. So you put in your sample, there's a pin, and it activates like the sensor that starts pumping down air from this region right here. Once that's all pumped down, then the sample gets entered into the actual column, which at that point there is no actual like pump that's pumping down air. It's what's an ion getter pump. Inside of here, he talks about the eucentric height, and that's the height at which, independent of the the stage tilt, there is no image shift. The image does not move anymore. And so each sample has a unique eucentric height that actually can vary within the same grid itself. So within the same grid, from square to square, bouncing around this 3 millimeter copper mesh grid, you can have, you know, changes of up to something crazy like 200 microns sometimes. So, you know, that's kind of a function of how flat your grid is. And yeah. So directions, can the sample move while it's in the microscope? So you can have translational movement, so X, Y, and then also Z. Airlock is the pre-vacuum area before it enters the column itself. Where does the sample rest with respect to the objective lens? The sample rests above the objective lens and above the objective apertures. The pull piece gap I'm going to skip because I did not find that very relevant for me. The cryo box, another word for the cryo box is actually the cold trap, and so this is kind of it's a piece that basically condenses contaminants inside of like the column. And so if you have any remaining residual condensation on the tip of your holder after you insert it into the column, because remember, once it's inside the column, there is no vacuum that's pulling off that moisture. So that's what the cold trap or this cryo box does, is it condenses it and pulls it off of the sample and helps to keep it clean inside of the column. And eucentric height is the height of the grid at which, when you're tilting your sample, there is no image shift. So, and it is different for every grid. Energy filters. So this is where it gets a little bit more fun. So energy filters are, and I'm only going to go over the post-column ones because those are the ones that I'm not actually even sure of any in-column energy filters that I've experienced. No.
There are mega filters. So we used to have a microscope called the
Oh.
So it was an in-column energy filter, and I think that's a secure type of energy filter.
Is it?
Yeah.
Can you explain why?
Because everything, I mean, it's all in a microscope.
It's on the microscope. It's not post. You're not adding something on post column.
Okay.
So it's within the optics. It's accounted for.
And is it more stable or?
It depends on the setup. A lot of these. So we brought up or I guess we talked about temperature. Since resistivity matters, your environment also matters quite a bit. So if you're changing temperature, you're changing resistance, you're changing, even if you have a constant current, you need to compensate with other types of devices to really have stable beam. So a lot of these additional features on a microscope will require quite a bit of alignment if you don't have a stable group. Actually, if you don't have a stable group, it might not even work categorically.
For a number of reasons, yeah.
Yeah.
I mean, the only reason why the Gatan is using a post-column energy filter is because of the patents.
They want to sell the camera with it.
No, the patents. They can't break the
You
Joule.
can't bring patents, right?
Yeah, so the Joule microscope company have the patents for in-column.
The
energy
Omega.
filter.
Okay, that's interesting to
So
know.
the camera company couldn't use that patent, so they had to do it after the column.
Huh.
So it's also hard to, you would have to have an interplay between different manufacturers. If you make cameras that go in the column, you have to place it within the column. So it'll have to be done during the build and design of the microscope. It can't be a choice. Unless you buy a microscope and you want a better camera with an energy filter. That's something, if it's post-column and separate from the system you add on.
Well, these are all very like technical things, but in theory, what an energy filter does is you have your electrons coming down your column, it hits your sample, and then it gets bent by this prism over here, And in an ideal scenario, the way that you're creating your images is by the elastically scattered or the unscattered electrons. Those are the ones that will add a lot of signal to your images. What you don't want is to have a lot of inelastically scattered images in electrons in your images, because that will just add to noise. And so what this energy filter does is after it bends your electrons, as long as the electrons coming in are the same energy coming out, then those are what enter the CCD. That's what ends up hitting your image and getting created. Anything that has a lower energy will get bent more severely, and now it will not go through the slit. So you can change the slit width anywhere from, I don't know, like 10 to 20 eV, so that you're just capturing your elastically scattered or unscattered events. And also it can be used in spectroscopy, so you can change that range so that you can see different like elements that excite at different, not wavelengths, changes in their energy loss. Yeah, something like that. And so this is what Ed was talking about at Yangtze, which is this post-column energy filter, which is here, and this is this omega in-column energy filter. So I guess if you have an omega, it's only going to be on a Joule microscope, and if you have a post-column, it's always going to be on a Krios.
You could put it on another microscope than Krios, but that's a similar idea.
Okay. So why are energy filters used? So that we can remove signal coming from electrons that have lost energy going through the sample, going through the column, through these inelastically scattered events. Post-column and in-column is exactly as it sounds. Typical slit width for Cryo-EM is generally about 20 eV. If you do something much tighter than that, because this system is very, very temperature dependent, if you shift off more than 10 eV and you have a 10 eV slit width, it can be very hard for it to find it again. So you want to kind of have it broad enough where you can make adjustments as temperature and things like that, fluctuations happen in the system. Zero loss peak is the point at which there was no loss in electrons coming in, and then what is detected on the camera. So that's the zero loss peak. And yeah, the energy filter allows you to image particular elements if the, I can read this a little bit more specifically. Producing an image using electrons that lost a certain amount of energy. So that's what you can use and it's part of like EELS, electron energy loss spectroscopy. But I don't think people buy an energy filter to do materials type experiments like that, but they could.
Yeah, so a problem we have with our Krios, we would not be able to do EOs because our beam is not really so bright. It's mainly for material science because the energy loss peak is very, very small compared to the distance of the beam. So you have to turn up your intensity really high. And that would cook most biological samples way before we can capture it. Also, with direct detectors, we try, even though they're radiation hardened, we try to limit the dose because we don't want to burn out the camera. But that's just secondary concerns.
Okay. Moving along, electron detectors. So this, I guess, would be kind of like the thing that makes EM so special right now, is this development in technology where we have these new electron detectors, these cameras that can detect single electron events. And so these are the different types of electron detectors that have been used historically. Photographic film, so basically there's like a film cassette underneath your specimen in the projection chamber. You record an image, and what the nice thing about photographic film is it's very large, and so you can resolve, like the resolution's higher. It's not great though because you have to develop it, you have to put it in and out of a vacuum system, and so you don't get the slow readout is probably the worst part of it, in that you can't get real feedback about what your data looks like, because you have to process it, you have to digitize it, so you can start processing it in silico. So it's not ideal, but again, it has a large field of view. TVs, fluorescent screen. The fluorescent screen is what it shows here. So this is like your sample would be here, and this fluorescent screen basically is made of a material that interacts with electrons, creating green photons. So a green light kind of emits onto this screen. So you can actually visualize your sample and your beam. So that's what the fluorescent screen does. And then the current technology, the technology that was most used was what's called a charge coupled device. And that's what these CCDs are. And now we're in the era of the direct detector. So CCDs are, what they do is you have incoming electrons and they hit what's called the scintillator, and the scintillator converts electrons to photons, which are then converted into a signal through the CCD. And so this two-step process can cause a large point spread function in what's like read out, and maybe Ed and you guys can kind of comment on this, but it ends up giving you, like, instead of individual events, it does what's like accounts of your electron events. And so even if like the way the electrons are scattered and read out in this fiber optic channel right here, you could have the same electron event be recorded as like a 40 count or a 10 count. So it's not very accurate in that sense. But CCDs are great because, again, really fast readout. They're very sensitive, and so like you get a lot of contrast in your images, and they have a wide dynamic range at which they can work. Disadvantage is especially from a photographic film, it's very small. So your field of view gets minimized. So in comparison, what direct detector technology does is, instead of using a scintillator to convert electrons to photons into a charge, it can actually just directly convert an electron into a charge and then digitize that for you. And they also are very special because they have a really, really fast frame readout, which helps in this. And this is a movie that he was showing where it kind of like records over a certain amount of time different electron events, and regardless of how intense each electron event is, because of the nature of like the readout, we can identify each one as a single electron event. So, and that can be more clearly portrayed in this image right here. So seeing a direct detector readout versus a CCD readout. The different types of electron detectors, which were the TV, the fluorescent screen, photographic film, CCD, and direct detector. CCD is a charge coupled device, and they work by converting electrons to photons to charge. And the disadvantages and advantages versus film. CCD is, film is larger, high resolution, but it's very, very tedious to work with and very slow technology, whereas the CCD has fast readout, high contrast, high dynamic range, but it's smaller field of view. And direct detection is just defined as being able to detect each electron event instead of converting it into another type of signal. What new capabilities do direct detectors provide? I think one of the major things about these direct detectors is that you can run in what's like called a movie mode. So you're no longer taking a 500 millisecond quick shot of an image. You can take like a 10 or depending on the camera, like a 10 or a 40-second movie, and correct for drift over that time. But it kind of increases the signal that you can get from each image and the resolution from each image. Vacuums, I'm going to just skip over all of this and just say that vacuums are very, very important in the electron microscope. Is there anything you want to add?
Well, basically vacuums are extremely important because I mentioned a little bit earlier, we're accelerating electrons at, could be up to 2/3 the speed of light. So we need to have an electron that's not going to lose any energy or interact with anything but your sample. So we need very only stuck at angstrom quality resolution. So if you had an optical microscope with that numerical aperture like that and any of those lenses, that'd be horrible. You're like, yeah, I have 500 nanometer wavelength of light. I can see things a few kilometers.
Yeah, that's right. Yeah.
So
It's a
with
good
the
analogy.
electron beam, it's like, okay, great, but we're stuck in the angstrom level. Fortunately, most of your questions are in the angstrom level.
Very good answer. Okay, so the last slides are going to be on safety. So it's a nice little diagram that just shows you all of the microscope. It's not very helpful because it's too much. The main things that I thought were helpful, so the purpose, there's like a heavy lead shield that's in all of our microscopes, and that kind of helps to prevent, to protect you from any like radiation leakage, like these electrons coming out. That could also, and these could happen when they backscatter from the sample or something like that. So there are like measures that they take to protect against that. Why do electron microscopes need chilled water? So those lenses that are being where a current is being applied to them can get very, very warm, and so you want to make sure you maintain that temperature by running chilled water around it. And so he's mentioned this a couple times through the lectures where like you can even have just people walking in the room and changing the temperature of that chilled water, and that can change the optics of the system. So it's very, very important that you have a very tightly temperature controlled system, both externally and both internally with these chilled water systems. Naming 3 lethal and at least 1 more non-lethal hazard associated with electron cryomicroscopes. So the obvious ones, liquid nitrogen, both gaseous and liquid, it can burn you. It's also can asphyxiate you. So those are 2 of the primary issues. Another cryogen that's worked with very regularly is ethane. So it's flammable as a gas, but it also is a burn hazard at liquid, which is what we freeze all of our grids with. On top of that, we also have the SF6, which is the gas that coats the jackets the high tension tank, and that is also an odorless heavy gas that can asphyxiate you. So a lot of things that can be potentially dangerous, but that any good lab safety should cover before you do any EM. And that's it.
There's one question from email. It's do accelerators impact the coherence of electrons?
Do accelerators impact the coherence? They should, right? Because, well, as long as they're accelerating them all uniformly, then temporal coherence should be good. Outside of that, I can't think of anything.
I'd imagine that's when there's a stack of them, right? Why you don't go from like negative whatever to ground to 0.
Sure.
Like, the series of them that sort of gradually steps everything up so that all of the electrons, at least
Are being
temporarily,
sped to the same speed, yeah.
are sort of progressing at the same rate.
Ed?
I actually don't know of how many electrons are coming out of the filament or actually going down the column. I don't know. That
Sure,
right.
probably like a very low percentage, right?
Probably a low percentage, because if you have a uniform source, it actually goes everywhere, like
Yeah.
but you only care about the ones going down the column.
Mhm.
And at any one point in time, if you're able to freeze time, I think there's only like 1 or 2 electrons in the column. We take exposures over seconds, so you might get hundreds of electrons per angstrom squared, so that's like a lot of electrons. But at any one given amount of time, you might only find 1 electron in the column. How many people have used an electron microscope?
Yeah.
That's what I was going to ask.
1, 2, 1.5.
Good. The practical should be interesting.
Yes.
Do you guys all have like Cryo-EM projects that you're working on, or this is more like for academic purposes?
This one eventually.
Yeah.
I'm getting there.
I think if you're doing any kind of structural biology, Cryo-EM definitely can answer a lot of the questions you might have now or down the line. So.
And if you're a crystallographer, you're used to producing proteins anyway.
Yeah.
Why not throw it in a grid? It's way easier than trying to get crystallized.
Which is what a lot of our newer users are from. an X-ray crystallography lab background. So it's interesting, the dynamics between crystallographers and EMers.
I think Youngzi and I both work in labs that do a lot of
Crystallography? Okay.
We're trying to like move into cryo-EM.
Oh, that's
Part of
interesting.
it,
I always thought that your labs were like the expert EM labs.
Oh, no, Larry's lab, I work in Larry Shapiro's lab at Columbia, who, it's me and one other postdoc do cryo-EM,
Okay.
but do all of our biochemistry, protein production, purification there, and we're bringing it here to EM. It's pretty, a lot of crystallographers are seeing the benefit now very quickly.
Right.
Trying to
Learning
save
off,
budgets.
piggybacking off of your experience. Yeah, for sure. Yeah. Well, if you guys have any questions or comments or anything, feel free to email me. I'm lkim@nyspc.org. Yes.
I have just one question. So
Yeah.
if you collect and choose from microscopes, then a lot of times you can actually combine
Combine the data? Oh, that's a great question. So it is not done commonly, but it theoretically could. So you are limited. So one of the things is each microscope is running at a certain magnification, which means that each pixel is some angstroms distance apart. So that's what you want to be the same, I think, primarily, right? So there are ways to get around that. One is working in what's called super resolution mode, which is what these direct electron detectors can do. So effectively, that's kind of like where you have a pixel and now you can split it into 4s. And so now you can be a little bit more accurate in like pointing to electron events. And then kind of, I guess, I haven't seen any combined data, like real data sets from super res across different microscopes, but theoretically it can be done.
There's only been a couple of users that published. Publish Lab has a major paper out. So the main issue that Laura pointed out is interpolation errors. So you need good calibrations, and you have to oversample one to minimize your interpolation errors. So that's why people collect in super resolution and for your bin down to what is necessary. So that's more on the processing side, but that impacts on how you're doing data collection. Also, it depends on the resolution you're aiming for. If you're 8-fold away from Nyquist, then you actually don't need to really do super resolution because you're oversampling. So it's more of an issue of oversampling.
Some of this stuff might make more sense when we go through the image formation and Fourier transform.
Yes,
approaches.
But what do you mean by oversample?
So let's say if I am aiming for a 4-angstrom structure and I'm collecting 0.1 angstrom pixels, then I'm oversampling by a lot. It's basically overkill. So there should be no problem with scaling at that point. Most people try to be more efficient and they oversample less. So a standard pixel size is a 1 angstrom pixel because you would assume you're trying to get into the near atomic regime, if not the atomic regime. Some people might be smirking because there's a big thread on CCP-EM and CCP-4 about what atomic
Really
resolution
means, yeah.
is. But that's really what so we tend to be quite conservative. So if you say that you're going to be at 2.5 angstroms and you only have an angstrom pixel and you're trying to scale an angstrom pixel, you may be closer to the Nyquist than you really realize, and you will impact your resolution. Then I would say collect the super S because then you're at least oversampling more than sufficient. All this to say that it just that question is more processing. So if you process it well, then it's not an issue.
Much more common to like combine data sets from the same microscope, right? Like one day, even in different samples,
Yeah.
grids that you stick inside. That's pretty common. Process a data set and say, oh, it's not quite the resolution I want. You feel like I need more angles, I need more data. So you make it a grid, stick it in the same microscope. That's pretty common for a lot of reasons.
Mm-hmm.
We've sort of been discussing all these issues kind of aren't the problem.
So scaling is not as much an issue as the performance of each microscope. I think what impinges on your resolution more is something you don't realize
The same microscope, yeah, absolutely.
How do you go to super resolution mode, like just or is that
Throughput is,
Resolution
yeah.
mode is easy. It's a camera setting. But the reason why most people don't use super resolution is it hurts data reduction because now you have 4 times the data. And yes, you can compress, but you eventually have to
Decompress it
decompress
to
work
process
with
it,
the
yeah.
image. So we don't have very good data. Crystallography has great data reduction. We don't have very good data reduction because we have images, and that's in real space. So within a couple of years, you can have a petabyte of data, not just your raw data, but you're going to process, right? So you in the EM field, you start to have to think about in terms of petabytes. Terabytes like nothing. You can collect a terabyte in a week and collect several dozen terabytes. But then that becomes an issue. So these are, again, a lot of the concerns I'm highlighting are ancillary to the main point where, yes, it can be done, but there are other reasons that seem unrelated that make it harder to do.
Maybe the point of super resonance. Big is not always better. I mean, a lot of new users or people coming in and just say, I want to go super res and everything.
Highest
Like
mag,
something.
yeah.
Yeah, but then if you just want to look at something that goes at 3x, you don't even go to that. And said every part of this pipeline will slow down with if you have something that's 4 times bigger, you'll slow down your collection a little bit, you'll slow down your alignments by a lot and everything and processing something really bulky. And at the end of the day, maybe your sampleology is not so good and it goes only to maybe even 8 angstrom. Then actually you've wasted all this additional time and effort to process something so big, but you're actually not getting there. Yeah, so it's so you don't have to go crazy and push all the way the limit from the go-get. That's the biggest
Yeah.
advice. Yeah.
So oftentimes when we do have users with like more like newer projects, we just tell them like do a standard collection with 1 angstrom pixel, and once you hit like a 4 or 5 angstrom or something where you're like pushing resolution, that's when you start throwing all the bells and whistles at your image collection and your processing. That's where you really want to get fine-tuned. But for initial reconstructions at about 4 to 5, you don't need all of that. So, and your processing will be much faster. And the sooner you have real data, the better you can start refining your grid prep, your sample prep, everything else that will get you a better structure. So.
And your biological question might be answered.
Exactly.
5 angstroms. You don't need anything less than that. I mean, everybody likes to chase that number, but if it's not necessary, then
Yeah.
why spend all that extra
Right.
time and money?
Okay. Thanks for your patience, everyone. I'm just gonna turn this off, Ed.
Yes.